selecting the appropriate trigonometric ratio. As we dive into the study of heights and distances, I want you to keep one primary objective in mind. In these types of problems, our goal is almost always to find an unknown length. This could be the vertical height of an object, like a building, or the horizontal distance between an observer and that object. To do this, we rely on two pieces of information, a known angle and one other side of a right-angled triangle. Now, you might find these problems a bit overwhelming at first when looking at a word problem, but here is a secret. The key to solving these efficiently and accurately lies entirely in your ability to select the correct trigonometric ratio. Over the next few slides, I will show you exactly how to identify your sides and choose the perfect ratio every single time. Welcome, everyone. Today, we are beginning a very practical topic in trigonometry, selecting the appropriate trigonometric ratio. Understanding the geometry of the problem. Now that we know our goal is to find an unknown length, let's look at how we actually set up these problems. Most real-world scenarios you'll encounter in this chapter, like measuring a building or a tree, can be modeled as a right-angled triangle. But before we can apply any formulas, we have to be very careful about how we label our triangle. To choose the right ratio, you must first identify the three sides of the triangle relative to the given angle, which we call theta. First, let's identify the opposite side. This is the side located directly across from the angle theta. In the context of the height and distance problems we discussed in the previous slide, this side usually represents the vertical height of the object, such as a tower, a building, or a tree. Next, we have the adjacent side. This is the side that sits right next to the angle theta, but it is not the hypotenuse. In most of our problems, this side represents the horizontal distance on the ground between the observer and the base of the object. Finally, we have the hypotenuse. This is always the longest side of the triangle, located directly opposite the right angle. In these practical problems, the hypotenuse often represents the line of sight. That's the diagonal path your eyes follow from the observer to the top of the object, or it could represent the length of a slanted object, like a ladder leaning against a wall. Once you have correctly identified these three sides, you'll be ready to move on to the next step, deciding which trigonometric ratio to use based on which sides you actually have. The decision process for selecting a ratio. Well, the choice of the trigonometric ratio depends entirely on two specific pieces of information: the side you already know from the problem and the side you are trying to find. Now that we understand how to identify the opposite, adjacent, and hypotenuse sides of our triangle, we reach the most critical part of the process, making the decision. You might be wondering, how do I know which formula to pick? Think of it as a matching game. You are looking for the one ratio that connects your known value to your unknown value. In the next few slides, I am going to show you exactly how to categorize these scenarios into three specific cases, so you never pick the wrong ratio again. Case A, relating height and distance, most common. Case A is what you will encounter most frequently in your exams. This happens when the problem gives you information about the vertical height, that's our opposite side, and the horizontal distance, our adjacent side, but it doesn't mention anything about the hypotenuse or the line of sight. In these specific scenarios, you should focus on the tangent or cotangent ratios. First, let's look at tangent. You'll want to use tangent when your goal is to find the height by using the distance you already know. Mathematically, we express this as tangent theta equals the opposite side divided by the adjacent side. On the other hand, if the problem is set up such that you need to find the horizontal distance using the height, you can use the cotangent ratio. This is expressed as cotangent theta equals the adjacent side divided by the opposite side. Now that we understand how to identify the opposite, adjacent, and hypotenuse sides from our previous slide, let's look at how to actually choose your ratio. Remember, the choice between these two is simply a matter of which side you are trying to isolate. As we move into the next slides, we will see how to switch to sine and cosine when the hypotenuse finally enters the problem. Case B, relating height and line of sight. So, when your problem involves the vertical height, which is our opposite side, and the hypotenuse, you should use the sine ratio. Mathematically, we express this as sine theta equals the opposite side divided by the hypotenuse. Now, let's move on to case B. Sometimes, a problem won't just give us the horizontal distance on the ground. Instead, you might be given the length of the line of sight. That's the diagonal path your eyes take from the object to your eyes. In the geometry we discussed in slide 2, this is the hypotenuse. Keep this in mind for when the problem mentions a slanted length or a direct line of sight, rather than just the distance along the ground. Case C, relating distance and line of sight. Now, let's move on to our final case. Case C. Sometimes, a problem won't ask you about the vertical height at all. Instead, you might be given the length of the line of sight, which we identified earlier as the hypotenuse, and asked to find the horizontal distance on the ground or vice versa. In these specific instances, where the problem involves the horizontal distance, which is our adjacent side, and the hypotenuse, you should use the cosine ratio. Mathematically, we express this as cosine theta equals the opposite side over the hypotenuse. Wait, let me correct that. Cosine theta equals the adjacent side over the hypotenuse. So, if you see the adjacent side and the hypotenuse mentioned in your problem, cosine is your go-to tool. We will see how to apply this logic in our upcoming examples. Real-world example, calculating the height of a mobile tower. Now that we have mastered the theory of selecting the correct ratio, let's put this into practice with a real-world application. Take a look at this scenario. Imagine a technician standing at a point, which we will call point A, on level ground. This technician is positioned 30 meters away from the base of a mobile tower, which we'll label as point B as the technician looks up from their feet toward the very top of the tower, which is point C. The angle of elevation is 60 degrees. Our objective here is to use the geometric principles we just discussed to calculate the unknown height of this tower. As we move to the next slide, we will break this problem down step by step to identify our sides and choose the perfect ratio. Step-by-step solution. In step 1, our first task is to identify exactly what information the problem has already provided to us. Looking at our diagram, we can see that the angle of elevation, which we represent as theta, is 60 degrees. We also have the horizontal distance, which is the side adjacent to our angle, labeled as AB, and this is given as 30 meters. Next, in step 2, we need to clearly define what we are actually trying to find. Our goal is to determine the height of the tower, which is the side opposite to our angle, labeled as BC to make our calculations easier. Let's represent this unknown height with the variable h. Now that we have the scenario laid out, let's move into the actual calculation by breaking it down into logical steps. By clearly separating what we know from what we need to find, we've set ourselves up perfectly for the next step, which is choosing the correct trigonometric ratio. Step-by-step solution, continued. Now that we have clearly identified our known value as 30 meters and our unknown variable as the height, let's move on to step 3, where we must select the most appropriate trigonometric ratio. Looking back at our definitions from earlier, we are dealing with the side opposite to our angle, which is the height, and the adjacent side, which is the horizontal distance. Because our problem involves the opposite and the adjacent sides, but does not mention the hypotenuse, the tangent ratio is our best choice. As a formula, we express this as tangent theta equals the opposite side divided by the adjacent side. Moving into step 4, we will now substitute our specific values from the problem into this formula. We replace theta with our given angle of 60 degrees, and we replace the sides with our specific segments, so we have tangent of 60 degrees equals the length of side BC divided by the length of side AB. Finally, since we previously identified the length of side AB as 30 meters, our equation becomes tangent of 60 degrees equals h over 30. Step-by-step solution, continued. Now that we have set up our equation in the previous step, we move on to step 5, which is where we actually solve for our unknown value, the height. First, we need to substitute the numerical value for our trigonometric ratio. We know from our standard trigonometric values that tangent of 60 degrees is equal to the square root of 3. When we plug that into our equation, we get the square root of 3 equals h divided by 30. To isolate h and find the height, we simply multiply both sides of the equation by 30. This leaves us with our final result. H equals 30 times the square root of 3, which gives us a height of 30 root 3 meters. In the next slide, we will review some common pitfalls to watch out for so you can ensure you're selecting the right ratios and setting up your equations correctly every time. Common mistakes to avoid. Now, before we wrap up today's lesson, I want to pause and discuss some common pitfalls. Even if you understand the formulas, it is very easy to lose marks due to small errors in logic or setup. First, let's talk about confusing the opposite and adjacent sides. This is perhaps the most frequent mistake I see. When you are looking at your triangle, don't just guess. Always remember, the opposite side is the one that is directly across from the angle theta. It is the side that does not touch the angle at all. If you misidentify these, your entire calculation will be incorrect. Second, be careful about using the wrong ratio. As we saw in our recent examples, many problems only provide the vertical height and the horizontal distance. In these cases, the hypotenuse is not mentioned and is not needed. A common error is trying to force a sine or cosine ratio into the problem when you should be using tangent or cotangent. If the problem only mentions height and distance from the base, your mind should immediately go toward tangent or cotangent. Finally, watch out for an incorrect ratio setup. Even if you have chosen the correct ratio, like tangent, you must ensure it is written correctly as the ratio of the opposite side over the adjacent side. If you accidentally flip it and write the adjacent side over the opposite side, you will end up with the reciprocal of the correct answer, which will lead you to a completely wrong value. Keep these points in mind as we move into our final summary of the key takeaways. Key takeaways. All right, we have reached the end of our lesson, so let's wrap everything up by reviewing the key takeaways to ensure you have a solid strategy for your exams. First, remember that tangent theta is your go-to ratio. In the vast majority of height and distance problems you will encounter, you are dealing with the vertical height and the horizontal distance on the ground. Since tangent theta links these two specific sides, it will be your most frequent tool. Second, keep sine theta and cosine theta in your back pocket, but use them specifically when the problem involves the hypotenuse. This usually happens when the problem mentions the line of sight or the length of a slanted object, like a ladder leaning against a wall. To make sure you never pick the wrong ratio, I want you to memorize this simple selection logic. If the problem relates height to distance, that implies you should use tangent or cotangent. If the problem relates height to the line of sight, that implies you should use sine. And finally, if the problem relates distance to the line of sight, that implies you should use cosine. If you keep this logic in mind, you'll be able to approach any problem in this chapter with confidence. Great job today!